Everyone, Dr. Crayhay here. In this lecture, I'm going to talk about hypothesis testing. So this is a topic that students get really confused about, and I think that there's good cause for that. It's because it is a very confusing and kind of counterintuitive system. Now, I understand that not all of us will be statisticians, so I'm going to try to just boil it down to kind of its basic decision framework. How do we use this in statistics to make decisions? I'll give you a little bit of extra stuff, but I'm going to try to highlight what you really need to know to move forward. So we have this problem where we have questions about large groups of people, right? We have these hypotheses, or maybe we want to know who are people going to vote for in the upcoming primaries, something like that. We don't have the time, we don't have the money, just in general, we don't have the resources to ask or to poll every single individual in the United States. So what we do is we rely on something called inferential statistics. And so that's what we're starting to get into. Hypothesis testing is the basis for just about every inferential statistical test. So we have to understand this to make our decisions. That's all this is. Hypothesis testing is a way to make decisions. It is a systematic way to decide whether results support a theory or if it's due to chance. So what we're doing is we're going to test a sample, so hopefully we choose a representative group to serve as our spokespeople, as our data points for the entire United States. We test a sample of maybe 100,000 instead of the entire population. And we choose those people very carefully, hoping that the results will generalize to that population. So how do we make that decision if these results are something that we should have confidence in, that we should take as research evidence, or how do we decide that this is just due to chance and we don't want to put any credo, we don't want to pay attention to these results because they're due to chance. Hypothesis testing is how we make those decisions. We'll get into some of the nitty-gritty on alternative hypotheses, null hypotheses, all of that stuff in a few slides, but first I wanted to speak about terminology first. So just because of the way that this system, hypothesis testing as a decision framework is set up, we do not accept the alternative hypothesis. We always reject the null hypothesis. So the idea is, if the null hypothesis, if you can't find evidence for it, you find evidence against it, you reject that, and then you just accept the alternative. But you don't say that. In terminology, when you write these things up, when you're talking about it, you always reject the null. You are testing the null hypothesis, which is why you focus on that. You're not testing the alternative for many reasons that I won't get into. It's more of a research methods issue. But anyway, the terminology is that we reject the null hypothesis. Alternatively, if you do not provide evidence, find evidence that way, you can't accept the null hypothesis either. So just because of the way the system is set up, you will not accept the alternative, you will not accept the null. You'll either reject the null or fail to reject the null. And we'll talk about this more in just in a second. Also, another note, and hopefully you picked this up in your research methods course, but in the social sciences, we do not prove anything. So as you're doing these write-ups, as you're discussing these results, please do not say that you have proven something. Behavior is just simply too complicated for us to say definitively when A happens, B will then happen, or whatever the research case may be. Instead, we provide evidence for things. So just a few notes on terminology there, some things to keep in mind as we push forward. So in this lecture, I'll lay out 5 steps of hypothesis testing. Your textbook is a little bit different. We're both saying the same thing, but I'm going to differentiate these to a more precise level than he did in the text. I do still encourage you to read this textbook, however. This chapter is going to help you. This lecture should be a supplement to reading that chapter. I think it'll clear some things up for you after you've read it. So the 5 steps: form a null hypothesis based on your research question. Then you form an alternative hypothesis based on your null hypothesis. You'll set the level of statistical significance, collect your data, get your test statistic, and determine your p-value, and then you'll finish it up by calculating effect sizes. So let's talk about each of these in turn. First up, you have a research question. You have some kind of research idea. Based on that, you're going to form a null hypothesis. To give you an overview, the null hypothesis will basically be the opposite of whatever you think is going to happen. So if your research hypothesis is that females are better at math than males, your null hypothesis would then be there's no difference in math performance by gender. So null is typically going to be no difference, no effect of whatever the research question is that you're talking about. So you always start with a research question. So say, for example, the town of Aubrey, Texas. So you guys know I moved to Indiana from Texas by now, probably. Say this town claims that their students have higher than average intelligence. So we want to investigate this question. So do students in Aubrey, Texas have higher than average IQs? We know from experience that IQ tests are normally distributed with a mean of 100 and a standard deviation of 15. So we can actually test this research question. But first we have to set up our null hypothesis. So like I said before, a null hypothesis will typically be one of no difference or no relationship. So you start with whatever your research question is. So you say there's a relationship between sugar consumption and weight gain. Then your null hypothesis is going to be the opposite of that. So in this case, it would be that there is no relationship between sugar consumption and weight gain. Going back to our students example, so Aubrey, Texas is claiming that they have higher than average IQs. So here we would say there's no difference between Aubrey students and the general population in IQ scores. Now there's some math symbols here. So HO, so I'll call that H sub O, is the abbreviation for a null hypothesis. So the null hypothesis is that, so here hopefully you remember this as mu. So we have mu for population 1, mu for population 2 equals 0. So the population of 1 minus the population of 2 is 0. In other words, these are the same, right? And so we could do this with sample terminology. So the sample mean minus the sample mean of the second group is 0. It's the same thing, right? So here in my example, we're taking the population values for an IQ test, and we're taking the population IQ score from this town of Aubrey, Texas. So there's no difference in IQ between Aubrey students and the general population. So again, H sub O is our null hypothesis. So we have mu pop, so that's going to be our population mean for IQ, minus the population mean of IQ for Aubrey equals 0. So again, null hypothesis is just stating that there is no difference or no relationship. In this specific example, there is no difference between the IQ scores of Aubrey students and the general population. Now the null hypothesis is what you will be testing. So this is what we gather data on, this is what we test in a hypothesis testing framework. So this is just some extra information for you to know and consider as you move forward and as you read or research. There are actually 2 kinds of null hypotheses. You can have a nil hypothesis or a non-nil hypothesis. What I just gave you in our last example is a nil hypothesis. It is a statement of absence. So there is no difference, there is no relationship. Overwhelmingly, this is what we test in statistics. So we're always testing against no relationship no effect, no relationship, no difference, all of those kinds of things. I shouldn't say always, but very often, I would say something like 98% of the time. You could also have a non-nil hypothesis. Here you would state that the difference is not zero, but you would give a specific difference. So perhaps you think that the IQ score is 5 points higher in Aubrey than the general population. That could be your non-nil hypothesis. You could be saying, so maybe in your alternative you would say, the difference in means is greater than 5, and so then your non-nil hypothesis would be that the difference is 5. But we don't test that. Our statistical programs aren't programmed to test that. So this is just some additional information for you guys to know and consider, that this is a possibility. You could do this differently, but people don't. Researchers don't tend to do that. Step 2, we have our research question. So we said that we think Aubrey has a higher IQ, their students have a higher IQ than the general population. Based on that, we formed a null hypothesis stating that the difference in IQ scores is 0, or that there is no difference in IQ scores between the Aubrey students and the general population. So here we're going to form our alternative hypothesis. The alternative hypothesis will be what we are interested in. It's really what we want to discuss in our research papers. It's the finding that we're trying to find. It's what the researcher is focused on. The alternative hypothesis represents the researcher's theory. So here we said Aubrey has a higher IQ than the population. So that was our research question, right? So what's the difference between a research question and an alternative hypothesis? Very, very little. Just how you phrase it, essentially. So a research question and alternative hypothesis, essentially the same thing here. So in our example, Aubrey has a higher IQ than the population. So H sub O, remember our null hypothesis is that the population IQ minus the Aubrey IQ, mean IQ, is 0. So there's no difference in these two IQs. So here we're going to say H sub 1, so that's abbreviation for our alternative hypothesis. So we'll say that the mean of the population, so the IQ of the population, is lower than the Aubrey IQ mean. We could say that they are not equal, so that would be what we call a non-directional hypothesis. If we just said they're different but we're not sure how they're different, that would be non-directional. In this case, I've given you a directional. Typically, we're going to test non-directional hypotheses. So we said that Aubrey has a higher IQ than the general population. That is what we call a directional hypothesis. So it's going to specify a range of values on only one side of the point prediction. So that's where you say one is larger than the other, those kinds of things. So we specified a directional hypothesis. Typically what we'll see in the social sciences, particularly at the undergraduate level, we'll all be testing non-directional hypotheses in this course. But it's going to predict any result that is not specified in the H sub O, which is null hypothesis. So in other words, we could have said in our example, this is what we'll test, the alternative hypothesis, that the IQ, so this is mu of 1, so the population IQ, mean IQ, is not the same as the population IQ for Aubrey. So we can have directional, we can have non-directional. Most of the time you're going to see non-directional tests. A directional test will increase power. So we'll talk about power in the next lecture. So maybe just jot that down in your notes and come back to it later. But basically it gives you, it makes it a little bit easier to find things when you know precisely what you're looking for. So that's an alternative hypothesis. The two different kinds, most frequently in the social sciences, we'll be dealing with non-directional alternative hypotheses. Moving right along to step 3, set your level of statistical significance. Now, this is pretty much set for you. So the cutoff for statistical significance will always be p is less than 0.05. So we'll talk about that in more depth, but just remember, p needs to be less than 0.05 to reject your null hypothesis. So this whole issue of statistical significance can get really hairy. It can get really confusing to the point that there was a study in the 1980s that investigated interpretation by undergraduate students, graduate students, research faculty, so people working on research, people teaching statistics courses, and they found across the board people are horrible at understanding statistical significance, interpreting statistical significance. That study was done in the 80s, and it does need to be redone. So actually, if you're interested in doing research on this, contact me. This is a study I would love to do. But if you contacted these kinds of people, they would still, I think, today be bad at interpreting this. What I want you guys to take home is that your rejection region, so for you to reject your null hypothesis, so we have this framework with a null hypothesis that says there's no difference. We have our alternative hypothesis, which is what we think is true, that there is a difference. We want to reject that null so that we can then claim that we have evidence for the alternative, right? To be able to reject our null hypothesis, we have to find a p-value less than 0.05. It could be p is 0.049, it could be p is 0.048, but if it's 0.051, then we fail to reject that null. So we'll practice doing these, but let's talk for a moment. What is a p-value? So here's a quote for you, but in essence, let's look at this this last line I have here on the slide. P stands for probability. Data is the data that you have gathered. We have a vertical line there, so that's it represents given that. H sub O is our null hypothesis, and then you know what true means. So p-value is the probability of obtaining the data that you have collected, given that the null hypothesis is true. So let's think about that for a moment. The probability of obtaining that data, so whatever data you're looking at, whatever test statistic you're looking at, given a true null hypothesis. Remember, the null is the one where we say there's no difference, there's no relationship, it's not the one that we want, right? So we don't want the probability to be very high at all. We want the probability to be teeny, 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 tiny, right? So people in the past have decided p less than 0.05 is our magic cutoff number. There's really no good reason, why not 0.06, why not 0.04? It's just 0.05. That's the way our culture has come to this day. So the probability of obtaining this data in a world where the null hypothesis is true. So you want that to be very small. You want that to be less than 0.05 so that you can reject your null hypothesis. So where do these p-values come from? Well, good news is you guys have already been finding them. So as we've been talking about the unit normal table, we've been finding the probability associated with a z of a certain value. You've been finding those probabilities. Those probabilities are our p-values, depending on the test. So you could start using hypothesis testing based on what you already know. So you have a z of 2.5 should you reject your null hypothesis. You could absolutely go ahead and do that with the information that you know today. Using those z charts, you can find those probabilities and you can decide if it's less than 0.05. Moving forward, we're going to be using, instead of z tables, which is what we've been using, there are t tables, there are f tables. We'll be using those kinds of things to calculate, or to find, really, our p statistic. In general, this rule holds true, right? So we have our normal distribution, and we'll have our test statistics going along here. So we know if it's a z distribution, we have a 0, a 1, a 2, a 3. Well, we also have a t distribution and f distribution that we'll talk about later. But we know things in the middle are very likely to occur. So that would be that it is very likely to get that data in a world where the null is true, which means you could not reject. If you are, however, in one of these rejection regions, or in the tail of our normal distribution, those are really unlikely events. So those are the cases where you're going to have p less than 0.05 and you can actually reject those. What this is showing you here is a non-directional two-tailed test. So when you say there's a difference, but I don't know which group is going to be larger, you have to split your p-value along your left tail and your right tail. If you said one group is higher, you could look for that 0.05 all on one side of the tail. So I'm not really going to hold you to those kinds of distinctions. We might have a couple of homework problems, but SPSS is going to test non-directional two-tailed tests in this way. So hopefully that makes sense. If you have any questions, please do reach out. Like I said, this is a confusing topic. So we started with our research question, and that was that Aubrey claims to have students with higher IQs than the general population. Based on that, we made a null hypothesis that there is no difference between the IQ of Aubrey students and the general population. We made an alternative hypothesis that there is a difference between the IQ scores of students in Aubrey and the general population. Now we need to collect our data and determine our p-value. So we just talked about p-values. We have to study everyone in Aubrey, get all of their IQ scores, and then we're going to calculate our z-scores and find a p-value to go along with that. So we know that IQ scores are normally distributed. The population mean is 100, population standard deviation is 15. Say that we collect all of the students, we collect data from all the students in Aubrey, and we find a mean of 112.8, and that's based on 9 people. And so here is our friend, the standard deviation, and you can see their number, their mean, is going to be out here to the right. So hopefully you're starting to see that this is a pretty unlikely event, that they're way out here. So this red line would represent where our general population is. That's the mean. This is pretty far away from the mean. So hopefully you have a general sense, just looking at this picture, what that z statistic would be, what that probability would be. If not, take a second, review that, think about what these numbers would be in relationship to each other. Our next step is to do your favorite thing, to calculate a z-score. So here we're doing things a little bit differently than we were in class because we're dealing with a population mean. So the equation changes ever so slightly, but we are doing the same thing. We're just trying to find the z statistic. And so we're going to take the mean minus the population mean, and then it's going to go over the standard error of measurement, which I'll talk about briefly, but I'm not going to hold you responsible for that information. Just know, in general, we're just calculating a z-score, just like we've been doing, so that we can find that associated probability. Okay, so I won't hold you to this, but for those that are interested, this is how I'm going to calculate the standard error for measurement in this example. So it's going to be the standard deviation over the square root of our n. So we're going to get 15 over the square root of 9, 15 over 3. Our standard error of measurement will be 5, and then we can plug that back into our modified z-score formula so that we can find that z statistic. So here we just plug in all of our numbers, so we know the mean of Aubrey is 112.8, the population mean is 100, our standard error of measurement is 5, and so our z statistic works out to be 2.52. So what do we do with this now? Well, now we have to find that p-value and decide if it's within the rejection region, so again if it's less than 0.05, so that we can reject that null hypothesis that there is no difference between the population and Aubrey IQ scores. So this is probably very difficult to read, but this is our good friend, the unit normal table, right? So we have our z-score. We know that it was, I believe it was 2.56, so we're going to go down along this left-hand column to 2.5, and then we're going to go over about 7 columns to find 2.56, the probability associated, this is to the left of a z-score of 2.56, and we find that that probability is 0.9948. So here we want to know the probability of getting a score more extreme. So what we're going to do here is take 1 minus 0.9948 to find that area in the tail. So our p-value is 0.0052. Remember, that's the probability of obtaining this data given that the null is true. That probability is very, very low. Is it low enough? So it has to be less than 0.05. Now I see students get confused about this all the time. So when you're interpreting this, I encourage you, I know it feels silly, draw a number line. Highlight where 0.05 is and then draw your number out and see if it's less than that, because people do make silly mistakes. I make silly mistakes all the time. So we have a p-value of 0.0052. Is this less than 0.05? Can we reject our null hypothesis? Yes, absolutely. So 0.005 is in fact less than 0.05. So we can conclude that Aubrey students have different IQ scores than the general population. There is a difference. So we reject that null hypothesis that is claiming that there is no difference. Starting from the top, we had a research question. We were wondering, Aubrey was making some claims that their students are smarter than average. Based on that, we made this null hypothesis stating that there's no difference in the IQ scores of Aubrey students versus the general population. We made an alternative hypothesis stating that, yes, in fact, there is a difference between IQ scores of Aubrey and the general population. We collected data, so we went down to Aubrey, we ran IQ scores on 9 students, we calculated a z-score using the population parameters for IQ scores in general, so mean of 100, standard deviation of 15. Using that data and the data that we collected, we calculate a z-score. With the z-score, we go back to our good friend, the unit normal table, find the probability of finding that score or a score more extreme, and we found that it was very, very small. So I think it was 0.005, which is less than 0.05, so we can reject our null and conclude that students in Aubrey, Texas are smarter than average. When we have a p-value that is less than this magical number of 0.05, we say that the result is statistically significant. Another note about terminology here. Please do not say that these are significant. To say that these kinds of results are significant implies something that we simply don't have information on yet. So when you are trying to express that the p is less than 0.05, make sure you go ahead and say statistically significant. That tells us that there is a difference here. So students in Aubrey, Texas are smarter than average. What a p-value does not tell us, unfortunately, because this is what we want it to tell us, it does not tell us how different they are. It's asking a simple yes/no question. Are they different? Is there a relationship? So that p-value tells us the answer to that question. If we want to know how different they are, so okay, are we talking about a 10-point difference? Are we talking about a 50-point difference? That we need a completely different statistic that is called effect size. So p-values will answer yes or no questions. Is there a difference? Is there a relationship? Yes or no. They cannot tell us how big the relationship is, how big the difference is. That is what effect sizes will tell us. Now, unfortunately, researchers do not report effect sizes as often as they should. So please, in this class, you will be required to use effect sizes. Make sure you hunt down what they are. Make sure you understand how to report them, and then put them in your paper. And remember, I'm here to help you through this process. So as you have questions, just reach out. Now, the difficult thing about effect sizes, it's not what they tell us. So remember, effect sizes tell us how big the difference is, how big the relationship is. The difficulty with effect sizes is that there are just so many different kinds of effect sizes. So when you're talking about group differences, you'll use Cohen's d. When you're talking about regression and prediction and association, you're going to be looking at things like R, R squared, those kinds of things. So there isn't one effect size across the board. So that makes it a little bit more difficult and might explain why these aren't always reported. In our situation, we want to know if two groups are different, right? So for that, we use Cohen's d. So Cohen's d as in dog, Cohen's d statistic. And we'll talk about this a little bit more when we talk about t-tests. But to calculate a d, you take the mean minus the population mean and then divide by the population standard deviation. In this case, the mean of the Aubrey students was 112.8 over, subtract to the population mean of 100 over the population standard deviation of 15. Our D works out to be 0.85. I believe your textbook gives information on how to interpret this effect size. A D of 0.85, that's probably a medium to large size effect. So a pretty decent difference. So we know Aubrey IQ students do have a higher IQ, and it's a pretty decent sized difference. So you want to report not only your p-values, but your effect sizes as well. And you have to be careful with effect sizes because depending on the test, the effect size will change. So that is an overview of hypothesis testing. So it's just a framework for making decisions. It has a set of rules that we have to follow, and hopefully it's a little bit clearer for you now. Be sure to leave any questions in the comments, and I will try to address those or record additional videos, find additional videos, whatever we need to do to help increase your understanding. In the next video, I'm going to give you some additional considerations, so talking about types of error, talking about power, those kinds of things. But hopefully you get the overall framework, which is to set a null hypothesis based on your research question, set your alternative hypothesis based on that null hypothesis, determine your p-value cutoff, which typically is going to be set for you. You're going to collect your data, calculate your test statistic, and find your p-value that is associated with that number, and then calculate your effect size so that you know how large that difference is, how large that relationship is. That, in a nutshell, is hypothesis testing.